Hello everyone, good morning. My name is Yuan Gao, a PhD candidate from the University of Science and Technology of China. The paper presented today is Alleviating Structural Distribution Shift in Graph Anomaly Detection. This paper studies a novel out-of-distribution problem called structural distribution shift and provide a simple but effective solution to it. The first part is the background of the graph anomaly detection. In the real world, the relational data could be modeled as a graph, such as product reviews and financial scenarios. For example, in the financial scenario, people, merchants, laptop, and phone, they are expressed as nodes, and the edges connected them together with the nodes, they form a financial graph. And the goal of the graph anomaly detection is to find nodes and edges deviate significantly from the normal nodes and edges, such as spam reviews or fraud transactions. And the main challenges of the graph anomaly detection is heterophily, whose definition is the number of edges connecting nodes belonging to the different classes. For example, in the homophily graph, the blue circles and the pink triangles are set apart with only a few edges connecting them, while in the heterophily graph, these nodes are mixed. However, unfortunately, in the graph anomaly detection scenario, most anomalies are submerged in the normal nodes, which makes the heterophily for anomalies higher than that for the normal nodes. As it can be seen from the table 1, the anomalies have a quite larger heterophily than that for the normal nodes. The existing methods can be categorized into two branches. The first branch is the resampling method. It picks neighbors according to the total neighbor label frequency. In this way, the center node will have a more balanced neighborhood distribution. And the second one is the pruning method. It prunes edges that connect nodes that are far away from each other. For example, given an input graph and the node features, a MLP is adopted to learn the representations of nodes. If the two connected nodes have a quite different representation, the edges connecting them will be pruned, and the pruned graph will be fed into GNN encoder to detect the anomalies out of normal nodes. The heterophily problem have been well addressed by the community. However, we found that the heterophily degree can vary between the training environment and the test environment. And the main reason can be twofold. The first one is the human annotation. As we all know that the human have a labeling preference of labeling easy ones and the homo nodes in our setting. So the homophily nodes will tend to appear in the training set, and the heterophily nodes will tend to appear in the test set. And the second one is the adversarial attack. We all know that many malicious accounts, they want to hide from the model detection. So they will use poison attack or evasion attack to disturb the distribution. So the heterophily degree between the training data set and the test data set will be different. And here's our motivation. The definition of the SDS means the label distribution of the neighborhood is different between training dataset and the test environment, which leads to different homophily and heterophily degrees for each node V. And according to our theorem, we found that the ideal objective cannot be accessed and optimized. Indeed, we optimize an objective evaluated on the observed nodes due to the existence of SDS. And here's a brief proof. According to the difference between the two equations, we conclude that the objective function cannot be directly accessed. Here is the methodology overview. Our model is called graph deconvolutional neural network. And the key point is to adopt different learning strategies for anomalies and normal nodes. For anomalies, we identify an invariant pattern that is not affected by SDS. And for normal nodes, we retain the benefit of GN neighborhood aggregation. Inspired by the variable decomposition algorithm, we separate the original node feature into two sets, the class feature and the surrounding feature. The class feature describes what the anomalies look like, regardless of the distribution shift. And the surrounding features describe the neighborhood pattern of normal nodes. To make it easier, we leverage two constraints. The class constraint makes anomalies close to the anomaly prototype and far from the normal prototype. And the connectivity constraint makes connecting nodes similar. Non-connecting nodes are dissimilar. To conclude, our model have three parts. The first one is the gradient-based feature selector. We separate the original node feature based on the absolute gradient score. We treat the features with top K gradient score as set class, and the others as set surrounding. And the second one is the prototype vector learning. We need this prototype to detect all the anomalies. So we initialize the prototype with the average feature of each class and update the prototype with cosine similarity during training. That is, if the node feature is close to the prototype, it will have a larger weight in the next epoch. And the third part is the other constraints. We leverage KL divergence to evaluate the similarity between two distributions. And the learning objective is GN loss plus lambda multiplied by the exponential of constraint loss. Because the constraint loss can be negative, so we use exponential to ensure the positivity of this term. And here's the experiments. We evaluate our model on two real-world benchmarks, and we adopt three metrics. These metrics are good for imbalanced tasks. F1 macro, AUC, and the G-mean. G-mean is the geometric mean of true positive rate and true negative rate. And can be seen from the table that our model outperforms baselines on two datasets over all of the three metrics. And our core point of our model is feature separation. So we analyze the stability of this process. According to the kernel density estimation and the heat map visualization, we can observe that the separated dimension is stable and almost unchanged. Our model is, and the aim of our model is to elevate the SDS problem. So we stimulate the human annotation and the adversarial attack setting. And we have x-axis as the normal setting and the y-axis as the best setting. So the blue dashed line means that the model have equal performance for these two settings. As can be seen from the figures, that our model, the brown one, performs the best. So to conclude, in this work, we explain a novel problem, structural distribution shift in GAD. It depicts the phenomenon that the heterophily degrees for the training set and the test set are different. To elevate SDS, we propose a novel method GDN. This is the first step to addressing the structural distribution shift in GAD. GDN works by separating node features into two parts. One ascertains an invariant pattern for anomalies, while the other endows with the ability to benefit from aggregation mechanism for normal nodes. And our model works in graph-structured anomaly detection tasks, such as spam reviews, fake news, and fraudulent ratings in e-commerce recommendation systems. Our model can work when annotated data is hard to acquire, and when data distribution is different, in different environments tends to be different. Okay, thanks for listening.